Hello, and welcome to this video on forces. We're going to be discussing what they do, what they are, and how we represent them on things like force diagrams and free body diagrams. The first and most obvious question to answer is, why would we even care about forces? And that is what they do. The answer is that they are responsible for every change of behavior of a system, by which we mean things like speeding up or slowing down, turning, or even deformations like squashing and stretching. So we can see that forces are quite important, but the next question is, what are they? They're essentially any push or pull on an object, like for instance trying to push or pull open a door. But even this simple definition immediately gives rise to some great insight, which is that a force has to clearly be an interaction between two objects. So forces require both an agent, which is an object that's going to exert the force, as well as a receiver, which is the object on which the force acts. So we often label these in a nice way, where we use subscripts to denote the agent and receiver. So FAR is our shorthand way of identifying a force by A, the agent, on R, the receiver. So in the case of the person opening the door, we might say F sub P D, the person is the agent, the door is the receiver. Okay, now thinking further about this person who's trying to open the door, we realize that this person has to actually make contact with the door, unless they happen to be telepathic, of course. So this provides a way of categorizing forces. The ones that require contact are very creatively named contact forces. Some forces do not require contact. These forces are called long range, and as an example, gravity is certainly long range. For instance, it holds the moon in orbit, even though, thankfully, the Earth and moon are not touching each other. Another example would be electromagnetic forces like magnets. Now, let's think about what are some examples of common forces and how we represent them. To do that, let's consider this commonplace, everyday situation here, in which we have a metal box that we want to push, but the metal box is attached by rope to another box. Also, the metal box is attached by a compressed spring to a wall, and also on the wall is a magnet. So there's quite a lot going on, but what we want to know is, what are the forces that are acting and how do we represent them? Now, one very obvious force that's going to be acting is the fact that we're pushing the box. We call that the applied force. And how do we represent it on the diagram? Well, remember, forces are vectors. Vectors have both a magnitude and a direction, so we're going to use an arrow to represent this force. And the length of the arrow will talk to us about the strength of the force, and of course, the direction that the arrow is pointing in should line up with the direction in which the force is being applied. So we have here that arrow. We're going to assume we're pushing quite strongly, so we'll draw in a long arrow pushing in the direction towards the wall as we push this box. Okay, another example of a force may not be the next one you'd think of, but since we're talking about pushes, well, there's clearly a push from the ground pushing up on the box, and that we call a normal force. It's because of the contact between the box and the ground, the contact of two surfaces, so we'll call it the normal force. And that normal force acts perpendicular to the surface, hence the word normal. Now, technically, we'd have to draw this in at every single point along the bottom of this box. So we'd have many little arrows like this, technically infinitely many, in fact. But of course, that would be really tedious to draw. And so instead, what we do is we imagine that we've just summed up all of these and figured out the average position where they act. And in this case, that just falls into the center with an overall strength that is the sum of all those little arrows. So we've actually already done this. Technically speaking, your hand makes contact at more than one point, but we only drew the one arrow. But we're going to do this every single time, so we're not too fussed by it. We can always just put an arrow at the effective location of all contributions to that type of force. Alright, now we've got two forces in place. There's still a lot more to go. So we're now imagining we're pushing this box. It's going to be sliding on the floor. If it's sliding across the floor, you know from everyday experience that things don't slide forever. There's clearly a force that acts opposite the motion. That force is the friction force. And again, technically it would be all along the bottom, but we're going to replace it with one big arrow that represents the sum of all the little bits of friction. And so we'll put that there. It's quite short because friction tends to be quite weak. Now, what else is going on? Well, there's this box that we're dragging. And that box is clearly going to be applying a force. That force, though, is actually transmitted by the rope. So the agent is going to be the rope, and ropes transmit forces along their lengths. So that sets the direction. So we've got this force in the rope, which we call a tension force, and it's acting in that direction along the length of the rope. Now, what else? We've got that spring on the wall. And springs are special little things that actually exert a force that opposes any change to its normal length. So this is an example of a restoring force. And what that means is if you stretch it, then it tries to exert a force such that the spring compresses back to its normal length. And if you compress it, then it tries to push apart so that it stretches back to its normal length. And we're told that this spring is compressed, so that means it's trying to push its way to spread back out, which means it's pushing our box to the left. So we can draw that in, and again, it's kind of small compared to our force, because presumably the spring isn't all that very strong. Okay, now all of these are forces which are contact forces. The question is, are there any long-range ones? And of course there are. We're sitting on Earth, so at the very least we've got gravity. Now gravity we represent as acting at the center of mass. That's the effective location for where all of this force is applied. So we draw one arrow pointing down from the center of mass. How do we know how long to make it? Well, that comes from thinking about Newton's second law. We know that this box is not accelerating up or down, which means that the sum of the forces in the up or down direction has to be zero, since the acceleration in that direction is zero. The only forces that are acting up or down are indeed that normal force that we drew in long ago and this gravity force that we're drawing in now, which means they have to be equal and opposite, and hence we know we draw the same length as we did for the normal force. Now there's another long-range force that's acting, and that is the force from the magnet, so this electromagnetic force of attraction. And we won't bother with the details, we'll just put that again at some effective location, which we'll say is roughly there. Okay. So that is a complete force diagram for this object. In fact, it's more than complete. In a force diagram, all we really need is the object itself and the various forces. So now that we've identified all the forces, we don't particularly care about all the rest of the information in this picture, which is to say the actual representation of the objects themselves. So we can get rid of those. Now, if we're not interested in even thinking about the rotational motion of this box, whether it perhaps tips over as a result of all these forces acting on it, then we can do something even simpler and reduce that box to a single point. and then just collect all the various forces and move them as if they're just all acting at that single point. This way, we can completely describe the translational motion in terms of what the forces are, so we can understand how this box moves left and right and up and down, but we've obscured away any information about rotation and things like that. This is called the free body diagram for the situation. Alright, so this video has covered quite a lot. We've covered the definition of forces, in that forces are what cause the change in motion of an object, and that they represent basically an interaction between an agent and a receiver. We've seen examples of several commonplace forces that you will encounter. We've seen that we can categorize them as contact forces and long-range forces, and that we represent them in different ways depending on what type of force we're talking about. Contact forces have to act at the point of contact, while long-range forces act at some single effective point. And we've seen that the force diagram shows all of those forces and where they act, and free body diagrams just collect everything to a single point. Hopefully this video has been helpful.